Okay. All right. So we're coming up on our census. So sorry for the heavy, statement there. It's really more for, obligatory communications. I think everybody here is fine. There's a few folks who have decided to try this class another time, and that's fine. But we are coming up on that. So please do help me with your attendance survey if you think of it. Um, let's see. So thank you to everyone who helped me figure this out. So sometimes I miss stuff. So the Newth sort is different and not the shuffle sort, and it's not even really. There is something called the Newth sort. It's more of a joke. It's like what's the worst sort you can possibly write? So this gentleman who was one of the early pioneers of algorithms, wrote something different than the Newth shuffle. The Newth shuffle is the randomization algorithm we looked at, which is linear and in terms of swaps. And so I apologize for that confusion, because if you look up sort of shuffle sort or Newth shuffle or Newth sort, it's confusing. So I was really kind of not helping you with your terminology. So I'll try to call it the Newth shuffle, which is also ironically called the Fisher-Yates algorithm. No relation to me, I can tell you. But anyway, that's that. I just wanted to clear the air on that. And the interesting thing about that one, just to remind you, is there's no compares on that, right? We're just doing the random swaps. And we'll see today that randomization can actually speed up algorithms. Sounds kind of crazy, but we're going to see that today. And it really is a strategy in a number of different algorithms for speeding things up. And we'll explain why. So we had our recursive guess. Everybody's doing pretty good on that. I'll probably get those and the homework assignments graded this weekend. It's going to be a monster weekend for grading, but I'll get everything done by midnight on Sunday, one way or another. So bear with me while I plow through that stuff. We do have a lab today called recursive differences. I've kind of made this up so that you can kind of explore another kind of recursion. So this is a bottom-up algorithm that I've invented. It doesn't really have a lot of mathematical meaning, but we'll talk about it today. And then, of course, we have our homework coming in about 2 weeks and our quiz. So just reminding you of that stuff. And I think we got a good introduction to that last time. So hopefully you at least have an idea where we're going with that. So today we'll just do a quick review, and we're going to do probably our deepest math of this semester, but it's really not going to be for the test. But I do think it's really important because it answered a question for me that was nagging at me for many, many years. We all take it on faith. We look it up on Wikipedia or, Geeks for Geeks or AI, and it says, oh, that sorting algorithm is n log n. We'll explain again why that might be n log n. But if you instrument your algorithm and you count up the number of times something happens, it doesn't ever exactly match. In fact, it doesn't sometimes even come that close. So it's like, well, what's going on there? So I'm going to go through the derivation, like why do they call it n log n? How do they know it's really n log n from a theoretical math standpoint rather than just an instrumentation standpoint? And it solves a little mystery. And for me, this made me feel so much better about algorithms, because I'm like, I don't want to just take it on faith because you're telling me it's n log n. I want to know, and I want to know mathematically, and I want it to line up with the empirical data like what we were generating on homework one. So if you'll, bear with me on the math today, maybe you'll have that same aha moment I did at one point where I was like, oh, okay, now I feel better about this whole thing. So then we'll look at our final sort and take a breather from sorting after this week. And this will be a recursive sort, very similar to the recursion pattern we explored with merge sort on Tuesday, but it's going to be, instead of from the bottom up like merge sort was, it's really going to be a top-down algorithm. And I'll show you what I mean by that when we dig into it. And then we'll look at, to close out the lecture, this really cool thing where you just go, well, yeah, that's really cool. I could sort. But if I was to tell you with one small modification, you could get a linear version where you can find the kth largest element in a giant list without ever sorting it, you'd be like, whoa, that's pretty good. Like linear is good, right? So we'll do that here shortly. Yes, question.
You touch up on like big O notation?
Absolutely. Yeah. So we're kind of laying the groundwork for that. Yeah. So whenever we talk about worst case, that's big O. So, and we'll explain why that's big O. Yeah. So yeah, I kind of do the empirical part of this course, and then we will definitely get into the theory. So big O, big omega, those traditional kind of math approaches to talking about that. Yeah. Fair and good question. So just quick look back so we don't forget. So we've traveled this journey so far. We saw the shuffle sort, which is the Knuth shuffle. So I should have fixed that slide. We looked at merge sort last time, which we said is a divide and conquer, can be a for loop or a while loop, but also can be recursive. And it is an n log n kind of performance. And we will also now look at quicksort, which is also n log n more or less. But if you remember merge sort, its best case, worst case, and average case were all tightly bound, which we said meant they were all right around n log n, which is kind of nice and predictable. We say that's a very tightly bound performance profile. Quicksort is not so tightly bound. It can go as fast as merge sort, but it can have a bad day where it ends up being almost quadratic in its worst case or big O performance, as we were saying there a moment ago. So interesting comparison. And we'll see here we used auxiliary memory. So it cost us some money. We had to buy more memory, but we got stability and we had a really nice tight performance profile. This one today, we don't need any extra memory, but we give up stability and we give up a possibility that we may have a really bad worst day performance. So a couple trade-offs, just kind of interesting to see. And then we'll kind of finish out with this Kth selection in our lab. Now, in merge sort, we saw last time merge base. So most of the meat of that program was how do I merge two really small lists of things next to each other in memory that are already individually sorted? How do I kind of put them together like sliding a deck of cards together that it's, so we get a fully ordered sort. So that merge process kind of bought us that n log n. Today we're going to look at a slightly different one where we have some different code that we have to write. Now remember, when we divide and conquer, we don't do the whole thing simultaneously unless we're on some awesome multi-core, multi-processor system. And even then, we probably still wouldn't go down all branches at the same time necessarily. So what we do typically is do what's an in-order traversal. So we sort of divide and we go down one side and then we come back up, and we'll see that that process here animated in a second. But when we think about the overall cost, we said last time, we have to imagine the whole tree, our full journey, start to finish, and ask ourselves, what was the cost of that full journey? So we have to think about how many levels do we have, which we said we can use the log base 2 if we're dividing things in two to get a pretty roundhouse sense of the number of levels. And then we have to have some intuition about, okay, well, how much did it cost on each level? And we'll look at that in detail today when we look at the derivation of this n log n thing here pretty quickly. But that's our divide and conquer. And, that kind of explains why we have this log thing floating around all the time, which we've said a few times, okay? So an in-order traversal, as we'll see very much in this course, especially when we get to nodes and things, is this what you're seeing here. We go left first, but we kind of have to explore all of the little cave paths before we can go up and go right again, okay? And all of that happens as a result of those two little lines of code that says recurse left, then recurse right, and then do work, okay? So that could be swapped. You could go right first and then go left and maybe accomplish what you set out to do, but it's going to travel through the tree, of course, in a different order. So we will see there are many traversal paths. There's really like 6 possible ways we could travel through this tree, which is kind of strange. But most of the time we go left, then right, recursively, and then slowly wind our way back up to the surface. Okay, so there was our code we looked at, and there's our merge base at the bottom. So we said, imagine kind of, you're not looping when you recurse, but you are kind of making a copy, and you're always going all the way to the bottom till here. And when you unwind, you come here and go down the right branch, right? And then up. Hard to visualize, I know, but think of that picture we just saw on the screen. That's really the journey that we're taking that whole time. Okay. So we are saying we just kind of travel all the way down until we got two little things and then we base merge them. And here I've got, a bigger example, base merging three things. Okay. So there's our fully sorted thing. So we'll see a little difference. You could swap this one with this one and you'd still get a working algorithm. It just would travel down the right side first, then kind of come back over to the left side. So no real difference there. Unlike our lab today, which does need you to follow a left traversal in order for it to come up with the right answer. Okay, get this annoying box out of here. Sorry about that. We don't really have any cost to our recursive part except this midpoint calculation. So my only point to make here is, yeah, you're probably right if you were to say, why aren't we counting that cost? Because that is an actual cost. But out of tradition, I guess you could say, we're just mostly focused on stuff relating to the array, comparison, swaps, all of that stuff. Yes, recursion does have a cost. It costs us memory. There is a cost to the midpoint calculation, but we kind of just throw that out the window. We don't worry about that because we're focused on the array. Okay. So I just wanted to throw that out there for you guys. So now let's imagine though, we won't do this, but it's kind of a fun question is how would you write the code to adapt this to a divide by three? Go down the left, go down the middle, go down the right, right? You just have to do a little bit more calculation, but you could do it. And now you'd have sort of a log base 3 kind of analysis, right? So we would use log base 3 to figure out the maximum depth based on n things, okay? So hopefully you kind of see the pattern there. Normally we don't do that for a variety of reasons. Log base 2 is often, divide and conquer in two parts is good enough, right? It gives us a big improvement, okay? But this would be a fun test question. I don't think it is, to be fair, but it would be fun. So let's look at the derivation of this n log n while we're at it. So bear with me while we do a little bit of math. You will not be tested on this, but I think it's worth your time because what we see is when we have this thing that we're going to sort here, we kind of have two sorted lists of size m that we need to merge together. We kind of said, there's a left side and a right side. The work that we do is the merging of those left and right sides. So we could just arbitrarily assign a cost, a worst case cost for that merge to be 2m minus 1. That's basically how many comparisons we need to do, okay? So now remember, m is going to change as we recurse down and get to smaller and smaller stuff. So I'm not using n as in Nancy here. I'm saying m as in mother so that we know the difference. This is a changing value, okay? So that's our worst case scenario, okay? So keep that in mind, right? And so just if you doubt that, just imagine we're somewhere in the middle of the array on some subsection, not at the left side, not at the right, and we're just merging it together into some auxiliary area and then copying it back. So that process, there's n cost or m cost right there. So that's 2 times m to copy those over. And our worst case scenario, if we compare everything and go through that merge thing, worst case, we're going to add another 2m minus 1, right? So that's compares on the right, and that's copies on the left. So, and then we copy it back again, and that's going to give us our 4m. So we're basically dealing with 4m total copies, worst case, and 2m minus 1 comparisons, okay? So we're going to just sort of analyze the comparison part of this as part of our analysis coming up. So that 2m minus 1 is just kind of a little mini equation you want to keep in mind, okay? So, but let's do something empirical here. So imagine we had 8 things. We kind of know roughly intuitively, let's just have some benchmark numbers. Log base 2 of 8 is 3 because 2 times 2 times 2 equals 8. And n times that, so 8 times 3 is going to give me 24. So just hold those numbers in your memory. And let's imagine the cost, the total cost of doing this merge sort. Okay, so the red arrows indicate a merge between two things that are size 1, right? And then we have a merge between another two things that are size 1, and then a merge between two things that are size 2. So each of those merges has this 2m minus 1 cost for comparisons, where m is the width of each side. Okay, so 2m minus 1, 2m minus 1, 2m minus 1, where m kind of changes all the time. But if I just manually count up the 2m minus 1 cost, right, and just kind of do it on a piece of paper, I got kind of like 2 times 4 minus 1, because m is 4, m is 4, right? So that's 7 compares, right? So then I do it over here, 6 compares. Really tedious to do, but if we add all those up, that's 17. That's less than n log n. So this was my big head scratcher in college. I'm like, come on, man. You said it was n log n. I can calculate n log n. That is not n log n. So what's missing? I don't understand, right? So this just really annoyed me. And so I said, okay, I kind of instrumented everything like we did in homework 1. And, I thought maybe there's a bug in my code. But no matter what value of n I calculated, right, empirically, I was always coming up short, right? 49 is definitely less than 64, which is n log n. So is it just I came up with some new algorithm that was too fast? That didn't seem very likely. But it turns out that, like so many things with algorithms, we throw away extra terms that are lower order. So an n log n term is a higher order term than maybe a linear term that has n in it. And so a lot of hand waving happens on Wikipedia and Geeks for Geeks and even AI, and they say, oh, it's n log n. But the truth is, it's not. It's actually something that we can calculate more exactly. But let's take a look at what's happening here and apply a little math. So we've got these terms. There's 1 term, 2 terms, 4 terms, 8 terms. So you can kind of see what's happening here. We have a geometric progression where we're scaling by 2 every time, not surprisingly. So the number of terms in our little equation there is sort of doubling every time, okay? And so there's a little hint. And if we look at 32 and we sort of simplify our numbers here, we're basically looking at 1 times 31, 2 times 15, 4 times 7, right? We're just sort of saying, oh, I got to do a bunch of merges here. So why don't I just, factor that thing out? That's the same kind of thing we were just looking at on the previous page. So those terms are the geometric progression terms. And this sets us up so we can do a little bit of swapping with some magic small equations to figure out what's going on here. Why and what is causing us to get to that 129, okay? So that's setting us up for a little bit of math. But let's look at the geometric series and get ourselves a nice equation we can do some plugging and chugging with. So for q terms in a geometric series where everything is getting multiplied by 2, we can calculate a couple things here pretty easily. And the equation that we would use for that is 1 minus the power of r raised to q, right, raised to the q power over 1 minus r. So if we simplify that, right, we're really getting 2q minus r, 2q minus 1 when r is equal to 2. And r is always going to be equal to 2 for us because we're dividing and conquering. So we got this nice little 2 to the q minus 1 equation we can maybe use to simplify a few things for us. So q, remember, is how many terms we have. But the number of terms we have is log base 2 of n. Aha. So what if we were to replace that q with log base 2 of n? What happens when we actually do that, right? Because that's the number of terms that we have. Okay, so if we sort of do a little more factoring here, kind of get ourselves ready for this, right? Those are the number of layers we have, okay? And we can sort of do a little bit of factoring here. How did we get to that? Okay, there's our, n minus 1, n minus 2, n minus 8, etc. okay, which is really 2 to some exponent power, okay, which is really 5n minus, right, for our, n equal 32. So we're still working with real numbers here. I haven't really, put in the plug and chug yet, but that's how we got there, right? That's how we got to the 129. But now we can swap in, instead of like locking it down to a 5, right? We can just put in the log base 2 of n, because that's how many levels we would have in the general case. So if we drop that in and do a little bit of factoring, we get 2 to the log base 2 of n, which simplifies to n, right? So what we're really seeing over here is the full true equation that everybody kind of waves their hands at. It's n log n minus n minus 1. This is really the exact worst case cost of a merge sort, okay? Now you might think, okay, so what? But it was bugging the heck out of me because I'm like, come on, it should match, right? If you're telling me that's what it is. It's just that in terms of algorithmic discussions, people don't talk about that. They just throw that away and say, well, it's n log n, right? And that's okay. But if anybody ever said, what is the derivation, you might want to try to remember, well, it's not exactly n log n. It's actually n log n minus n minus 1. And now the numbers match, right? Now we can actually see our empirical results matching exactly up with that equation, okay? Because we're always short by n minus 1 of the full, log base 2 times n. So I was like, oh, thank goodness, finally, we didn't have to do a ton of math. We just needed to remember a geometric series and an identity function for, 2 to the log base 2 of n, and things kind of worked their way out, okay? So that's kind of, for me, that was an interesting mystery. And it shows us kind of how algorithms are really analyzed sort of mathematically. There is a way using various approaches to actually, tease out these equations without having to do the empirical stuff that I kind of made you guys all do for your homework 1, right? And so although we won't really get too deep into that in this course, you may be interested to know that if you go deeper in algorithmic analysis, that's really one of the ways in which you'll get more advanced, is understanding how to do that stuff in a more mathy kind of way, okay? But that's, a way to get there, right? And you can kind of come back and take a look at this. We're not going to test you on that because we're more interested in the code and the data structures here. But that's what we call linear arithmetic. It's just that we kind of ignore that part of that because it's a lower order term, okay? So we use just a couple things and we can kind of, factor out stuff. And that's really good for powers of 2, right? It's sort of easy to demonstrate where n is a power of 2. Proving it's true for other values is a much more elaborate mathematical proof. So when people go study algorithms, at a higher level, they are trying to prove mathematically that these things are as fast as they can possibly be, okay? So there's a rigorous proof that's separate from all the empirical data that has to actually be done, okay? So that's just a little bit of peek at where you go with algorithms, I think, if you keep digging deeper. But we're going to pull back then and get back into the code and slowly, head over toward data structures starting next week. But this is our last sort, so let's kind of look into it and see how it goes. This one is quite a little challenging to visualize apart. So the idea here is we would like to pick a pivot, and we don't want to sort the data right away. We want to partition, and partitioning means, moving stuff to the left side of the 5 that is less than 5, and moving stuff to the right side of the 5 that's bigger than the 5, and doing as little work as possible. Don't sort, just swap, okay? And try to do it without any extra memory, except for like maybe one integer, right? A temporary integer. So that means we're going to swap. So partitioning is like a partial sorting, if you want to think of it that way. And for the moment, pick whatever number you want. And we'll talk, about strategies, but we have big brains. We can look at that and go, oh, yeah, 5 looks like that'd be a good number to pick, right? Because it's probably somewhere in the middle. Okay. So we can do that quickly, but if you had a million numbers, that's a little trickier problem. And we'll talk about that in a minute. But let's just go with the 5 for the minute. So anything that's less than 5 goes to the left, anything that's greater goes to the right. We'll talk about how we do that, but that's what we call partitioning. Okay. Partitioning. And so everything, and you got to just conventionally decide where the duplicates go. So if there's a 5, do we move it on the left or the right? If there's an extra 5, do we move it on the left or right? It just depends. We'll say it's going to go on the right. We'll put duplicates of the partition on the right for this class. But you could choose either convention. Okay. It's not sorted. It's partitioned around the 5, and the 5 is in its final resting place. So that's something that sometimes gets missed. So think about this. We know now for a fact that 5 no longer needs to move. It's done. Okay. That's kind of cool. Okay. It's in its final place, even though everything else is still kind of a mess. That's a really important fact. Okay. Now, unlike the merge sort, we do not need to look at that number 5 position anymore. So if we recursively work on the left half, it's going to be 1 minus what we call the pivot position, that pivot position that we're pivoting around, and 1 plus, okay, not like merge sort, and we'll take a look at the code again. And so then we just say, okay, do that same thing again recursively with the left side. Okay, so pick a number, pivot around that, put it in its final position, recurse, and go down left, 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 right? And then come up and slowly chip away at the portions which we haven't fixed yet. And eventually we'll finish that side, right? So let's say I pick 2 as a midpoint there. Well, the 1 needs to go left, 2 ends up in the middle, right? And the 4 and the 3 kind of go to the right. And then we go work on the other side, okay? So it's different. It's kind of top down, where the merge sort was bottom up. We were merging the 1 and the 1 and the 2 and the 2. Here we're pivoting or partitioning around the pivot point from the top down. Okay. And I'll explain in a moment why I keep picking the 1 at the far left, which seems like a silly thing maybe when you first look at it. Okay. So let's just break it down a little deeper. So here's a full sort, and I won't do this more than once or twice because I know it's tedious, but I'm just going to arbitrarily say, oh yeah, that 5 looks good over there. So what do? So we're going to partition around the 5, not sort. Then we're going to recursively go down the left side. So you can kind of see where these things came over, right? And then we're going to pick the 2 and work on those. Okay. So the 1's got to come over for the 2, right? And notice we just keep drilling down until we get down to, the bottom there. So I partitioned it around the 2, right? And there's the other things there that go to the right of the 2. Notice they're not sorted. Now, when I get down to something of size 1, it's kind of obvious I don't need to do any more partitioning. And we'll look at the code in a second. So we're done over here. The green boxes are done. Go up to the right, partition and, around the 4. Get the 3 over where it goes. Now the 4 is done and the 3 is done. Now the entire left-hand side and the 5 are in their proper positions. Okay. Partitioning on the way down. When we unwind, our work is done. There's no work to do on the unwind. Merge sort was different. Merge sort, the work happened on the unwind on the way up. Okay. So that's our left sort, and then we just sort of continue. Okay. So this is the hallmark of our quick sort algorithm. Okay. So let's try this. We can do it digitally with our cards. But we're going to deal out some cards. I'll start with fewer cards just to show you. And again, feel free to grab cards if you want, or just use your digital deck there. But let me try to show you this. Sometimes it's trickier than it looks. So let me do this. Sorry for blinding everybody with that. Let me zoom up a little bit. Can I zoom up? No, we'll just go easy there. Okay, let me try 4 cards for start. Okay. All right. So now with my big brain, I can kind of see what might be an ideal middle card, but I'm just gonna kind of play it dumb here and say, oh, I'm gonna pick 9, you know? So 9 is the middle card. Okay. That's that's the middle card. So I need to get these things kind of worked left and right. So I need to find 2 things that I can swap so I can get this section over here ready to bring the 9 in at the very last minute. Okay. So how do I do that? Well, I don't want to swap the ace and the 2, right? Because that's not really doing any good work, right? But I could swap the 7 and the ace, right? So that's a fair swap. Remember, I don't really have any extra memory here. Okay. And now I'm done, right? I've got things kind of arranged with big stuff on the right, little stuff on the left. And the last thing I'm going to do is swap that ace with my partitioning value. Okay. And now I'm partitioned around. Sorry, whoops, I goofed something up here. Sorry. I I'm gonna swap. I'm gonna swap the 7. Sorry, swap the 7 with that partitioning value. So I'm now partitioned around the 9. I got nothing over here, but I am validly partitioned, and I don't really have much to do on the recursing on the right side of that 9, but I do have some recursion to do on the left side here, right? So sometimes picking this number over here, if it's not a median value, is going to give me an unbalanced tree. It means my recursion is not going to be like really nicely balanced, like that merge sort picture we saw. It's going to be like lopsided. And that's just the luck of the draw, right? Excuse the pun, right? We picked that 9 arbitrarily and it ended up being not a great pick. Okay. But, we still get the end result. Okay. And eventually things shake out. So let me just do one more for you. So I'll do it with 6 cards this time and see if I can get it right. Okay. So here's our 6 cards. Maybe I won't get a joker. Okay. All right. So I'm going to pick the 5. Okay. And I'm going to say, okay, that's going to be my middle card. So now I need to find pairs to swap. So I'm going to work from this side in and this side in. So these two look like they're on the correct sides. The jack and the 4, not so much. So let's swap the jack and the 4. Okay. All right. And now we move in over here, right? And we've kind of closed out on the same card. That means we're done. So what we're going to do is swap the thing just to the other side of that with the pivot card, and we're done, right? We are partitioned, okay? We didn't need any extra memory. We're ready to recursively break down the left side, do the same thing, break down the right side. It's kind of weird, but we'll go over why we choose the left side and what it means to try to do something different in that situation, okay? But that's what we call partitioning, okay? So very helpful to kind of get your heads wrapped around that part before we get to the recursion part. So one of the things we saw is if we pick something by accident that's either the biggest thing or the smallest thing, then we're probably not going to need to move any cards at all. It's just sort of a bad situation because we didn't divide our work in half. So it's like, okay, well, we kind of wasted some energy on that one. Okay. And if we wanted to sort ascending versus descending, it's a pretty simple change, right? Because we saw this before in the merge sort. We just changed the comparison, right? We say, well, instead of looking for something that's greater than something, we do the less than. So that's pretty trivial, okay? So we just change from the -1 on the compare to the +1. So the ideal pivot, though, to give us the most optimum quicksort ever would be the median card, right? So if we could figure out what the median card was at any recursive level, we'd probably have a really efficient sort, almost as efficient as merge sort. But the only way to really know that is to sort stuff, right? Kind of. So, but sorting costs us n log n. right? In the best case that we've seen so far. So doing that a whole bunch of times is not n log n. It ends up being n log n times n, right? So we're back to quadratic. So we can't really sort the data to find the median value. We're kind of stuck. So what do we do? Okay. So, because that would just be ruining, our whole idea of sorting or, doing the sort. But it turns out that if we randomize the cards ahead of time, every card has an equal chance of being the median value. And as you get to smaller and smaller sections, you get luckier and luckier, of course. So, and we know that we can use the Newth shuffle and only pay a cost of n one time. So it's like saying plus n on the end of our n log n or whatever the cost of this quicksort is. So very often the cost of n to randomize stuff can lead to an optimal larger term, right? Instead of quadratic, it could lead to something like n log n, which is the case for quicksort. So one of the strategies we'll do is we'll randomize the cards before we actually attempt to sort with the quicksort algorithm to minimize the chances that we have a bad day, that we hit our worst case quadratic result. Okay. We could still do it, but the odds of doing it go dramatically down. Okay. Now, there are other strategies for finding the median. We could randomly pick 3 cards and do a 3-card sort, just like you did on your previous lab, right? So if I say, hey, pick 3 cards at random and then find the middle one, then, or put them in order and then find the middle one, right? That's your best pivot pick. That's a good strategy, right? That's okay. It's not a really expensive thing. We're not sorting. We're just sort of trying to improve our chances a little bit. So there are a couple different tricks, but pre-shuffling things ahead of time, right, is probably the best way to do it. Okay. So what we do is we pre-shuffle and then we just say, let's go with the card in the leftmost position because it's got an equal chance of being the best median, right? And giving us a balanced recursive traversal. Okay. So that's why I kind of pick that left one every time, is because I'm assuming we've randomized the card ordering ahead of time, and it's just as good as just about any other strategy I could come up with. Okay. And that's a pretty traditional thing to do. Okay. Pick the leftmost card, sort these things kind of left and right side using swapping only, and then at the last minute, bring that 6 into its final position and repeat the process recursively. Okay. So this is basically the full quicksort. It's the partitioning step, and then the recursion part actually is relatively straightforward. Okay. So randomization helps us, which is really good. We could get a bad pivot, right? It could like slow us down, but we have less chance of doing that. And a good pivot actually is like a balanced tree, right? We go down all sides equally. We have a shallower tree. We have not as much depth to our stuff that we have to do. Okay. So these are just sort of some of the stuff I think we covered, but we're still going to have roughly n log base 2 of n divisions or log base 2 of n levels on average. Okay. So that's actually, if we pick a really good median most of the time. If we do a really bad job, we have a linear depth. So imagine that every time I pick the left card, it ends up being the smallest card. So then we just end up creating this lopsided tree, and we only deal with one thing every time. That's going to be n levels, not log base 2n levels. So partitioning in quicksort should lead to a nice tree that's log base 2 of n, but it can lead to a deeper one. Now, we don't need any auxiliary space for this, so that's a really nice thing. So maybe we're on an Arduino or something with constrained space. So we want an algorithm where, we don't have to have 2n of the array size. But we lose stability. All this swapping we're doing is definitely going to break the stability. There's kind of no way around that. So we give up some things and maybe we don't even really have the greatest performance, okay? But let's take a look at this. It's a little hard to follow. I'm just gonna show you the video, but you can definitely go over here. And remember that when you go over to visualalgo.com, there's a lot of really cool things out here. So like if you go all the way out to the top, pretty much every algorithm's here. It's pretty wild. And we'll explore some of these over time. But remember to pick the QI for quicksort, and then just go ahead and sort, okay? And choose show depth. You'll see the pseudocode up there. So there on the left, the yellow thing is the thing we picked to be the median. So we're trying to sort stuff left and right of the 22 and then swap the 22 in. And then we recurse down and do that with the yellow 7. Like get it in there. Now swap, get down. We're done there. Okay. Are we done there? Yeah, we're done there. Okay, put it back. Okay, now get over there. Go left and right of the 23. Bring the 23 in. Repeat on a recursive level. And that's our kind of quick sort process. Okay. And remember that what's really cool is every time we pick a pivot, that number is in its final resting place. And that's a real key to our final example today after our quick sort. So we'll come back to that here in just a minute. You can also look at these videos. I think in the quiz that's coming up, it's a little bit lame, I admit, but you'll see these videos in your quiz and it'll be like, what sort is that, right? So it helps to kind of look at these things and watch them play out either on Visual Algo, or you can come back to this video and play it. I think I didn't enable security, external links in my PowerPoints today, so I can't unfortunately play that video for you, but you should be able to play that or click on the Visual Algo link there and kind of do the same kind of thing, okay? And it's kind of cool to watch if you come up with a really large number of things. So here's just one more representation of how this algorithm works. Start at the top, pick the 5 arbitrarily, we partition. So I'm kind of waving my hands here and saying we did the partitioning. 5's in its final resting place. Then we go down the left side at the 1 minus the pivot position, right? From 0 to position 4. 0, 1, 2, 3, 4, right? Position 4 in the array. This is conveniently 5 ended up in the 5th position. That was intentional for me, right? But then we go down that side, right? Which we divide in half again, and we got the pivot there. So we go down 0, 0, which is a trivial case. We don't do anything. We come back up. We come down over here between 2 and 4. Now, for those of you, think about your midpoint. The midpoint is not, n over 2. It's starting plus ending over 2. Or, 2 plus 4, that's 6 over 2. That takes us to position 3. 0, 1, 2, 3. So we're always working in the full array, whether we realize it or not. So that's why we send in the start and end so that our midpoint calculation works, okay? So we're not just saying 3 divided by 2, we're saying, take 6 and divide it by 2, okay? So we get our pivot, we break it down, and now all of those orange things are done. So really, the left half of our array is done now, right? So even though we're just recursing and unwinding up to the top, we've already fixed the array because our array is passed by reference and we just kind of fixed it on the way down, right? So everything on the left side is done. And then we just repeat that on the right side. Pick a pivot, break it down, go the other way, and unwind. And now we're completely done, okay? So it's a little bit of a crazy algorithm, but interesting, how similar but different it is to the merge sort that we saw last time, okay? And we'll take a look at the pseudocode here now, right? So keep in mind, there's only one array this time, where with merge sort, we had a copy in and out of auxiliary space. Here, we're forcing ourselves to use swapping in order to avoid the extra memory. So quicksort was invented back in a time when, memory was, critical and not cheap. And merge sort was probably frowned upon. Nowadays, merge sort probably wins. But let's take a look at the code. You give me an array, you give me the sub-region, start to end, that I need to work on. And if that sub-region is greater than 1, I'm going to call the partitioning function and say, hey, go work on this thing left and right. Tell me what your pivot index was. And I will use that as I divide and conquer the rest of the array. Go down the left side from start to pivot -1. Go down the right side from pivot +1 to end. So notice we do not include the pivot point in that range for the left and right sides. And that's it, right? All of the work happens on the way down, right? Do some work, go left, right, circle around, kind of, do some work, go down, and build that tree. Always hate this stuff floating around there. Okay, that out of the way. So we figure out about the final position of the pivot, right? And that's done, right? So that's a clue that we'll use in our final little thing at the end of the class here for case select, okay? So that's our recursive code, right? Let's take a look at the partitioning code real quick, okay? Keep in mind, you could switch these two lines of code and you'd still get the correct answer, but you definitely don't want to switch this, right? That's got to happen first. We do that work because we need the position before the pivot so we can use it in our recursive pass, okay? So we can swap the left and the right and everything should work out. So just a quick peek back at the merge sort. So notice there, we have an auxiliary data array we need. Okay, we have the start end. We calculate the midpoint and divide first and do the work on the way up. And we do include the midpoint in that work. But otherwise, pretty simple, right? Pretty straightforward in this section of that code, right? So let's take a look back one more time before we look at the partitioning, right? Do some work, branch left, right, unwind, we're all done. And there's the merge sort, okay? So those are our two fastest sorts. Most sorts are using some form probably of one of these two or a hybrid. So if you have a library sorting algorithm in Python or Java or C++ in a library, it's probably using one or two of these, but you want to know which one, right? Because one of them's not stable and the other one is. So if you want to sort multi-column data, you would not use a quick sort. You would use a merge sort. So it's an important question, okay? So again, this optimal partitioning thing, we said if we just, pick that thing, then, optimal partitioning. How do we do it? We assume that we've randomized, we hold that pointer to the side, and we kind of work on this section here before we bring our pivot value in. We move the left thing inward while what's at that location is less than the pivot point, which is our array start, right? So we're moving that thing to the right with an L++. At the same time, we're moving the right thing to the left while it's greater than the pivot point all the way at the start position, okay? And we're looking for a good swap. So if what's at the L and the R are swappable, we'll swap and then we'll repeat the process. Okay? That's what we're doing to kind of do what we were doing in the cards. And basically, if these things cross, if the L and the R cross or land on each other, we know it's time to do our final swap, right? So we kind of move over one more and then use that to swap, and we're a partition. Okay, we've broken stability, but we didn't use any extra data except for one, or memory, except for one little integer for scratchpad. Okay, and then we say, oh, that is what people need to know about. So let's return that position to the next higher level of recursion, so it can be used, so it can be used to do recursion and not next higher, next lower level of recursion. Okay, and I'll show you that in the code. Okay. Now, we've kind of seen this, but let's just kind of walk through it real quick. We're going to swap the left and the right. Sorry, I rewound on you there. Okay. So I swap the 1 and the 8. I keep moving until I find a good match, right? Keep moving until I find a good match, swap. Okay. Keep going, swap. As soon as they land on each other, we know we're kind of done. And we move the R over one more. Oh yeah, if they're equal, then we just swap it with that one and it's okay. Yeah. Okay. And then return the position of that 0, 1, 2, 3, 4. Okay. Still not sorted, but partitioned. Okay. Another one. And if you're curious about this, these things are interesting, but we're mostly going to look at the code and kind of take it on faith. But bear with me for one more here, and then I'll let you dig through the last. So here, we want to say, okay, we've got a 5, right? We want that to be our pivot. So we're looking for the first thing that's greater than a 5. And the right thing, we're looking for the first thing. Whoops, do that again. Right thing, we're looking for the first thing that's less than the 5. Well, they crossed. So that means we don't really have any work to do. We just sort of swap in the pivot position and get the 1 out of the way, and we're done with that. So that may be one of the more tricky ones. But let's cut to the chase with the code. Rather than going through example 3 here, you can come back and do that. But this is just kind of working it out slowly. I'm going to skip over this too, because you guys can do this on your own, because I want to save us some time for lab. But essentially, the code, will bring it home for you. So there, again, is our quick sort recursive portion. Just quick look for you. And you can click into this code and run the solution if you want. But let's look at the partitioning code for this. Okay, remembering we don't include the pivot in that. Okay. So here's the partitioning code. So remember, we send in the start and the end array position. We start on the left side and the right side, the end plus 1. Now this is a little tricky. There are lots of formulations of this partitioning code, but we're starting out of bounds with the left and the right, and we're going to pre-increment plus L. So we're saying, okay, move into position before we do the comparison. That's just the way this particular version of this partition code was written. We start out of bounds on the starting and beyond the end of the array, and then we pull it back, okay? And then we check to see if we've crossed, right? If we've gotten to the end with the left, then we're out. Otherwise, we'll compare, pre-decrement the R, right, before the comparison, right? Keep going until we kind of find a place to break. And if they cross, then we break. Otherwise, we're going to swap, right? It's time to swap. And then we keep going in the while loop, right? We keep closing in from the left and right sides like we saw we were doing until we cross, and then we break out. And then we swap in the starting position with the R position, the right side position, right? And we return the position of the pivot. So nobody's going to expect you to memorize this, right? That's not the point. It's like a card trick. It's like somebody really worked hard to figure this out, but you should appreciate it. Our job here is not to have you memorize this stuff, but to sort of get the pattern and to be able to think about the whole strategy we have here. So this is what's happening just to get that thing swapped into its partitioning position. And then recursion takes care of the rest for us, okay? And then there's just a little code trickery here where we're using this pre-increment, but there's lots of ways you could rewrite this so it's not doing that kind of a sketchy thing. But that's some pretty optimal code right there, okay? That's probably about as fast as you could do it, I'm guessing, assuming we just have pre-randomized everything and picking the leftmost thing is the best guess we can make. Okay. Now we could take this section, last comment on this, sorry, I had to drag it out. We could take this section here and say, yeah, I'm not good enough with just that. I want to pick 3 random numbers from inside of the start end range, find the middle position, and use that one as our pivot. You could do that too, right? So that's going to change this algorithm a little bit, but it might give you a better result, okay? But most of the time we just randomize, pick the leftmost thing, and get on with it, okay? So our performance on this, as I mentioned, right, assuming that we randomize first, is going to minimize this really unbalanced tree traversal where one side gets really lopsided, okay? Now, you could go with the leftmost index or the rightmost index, it's not a lot of different code, but you're still going to end up swapping and, getting things into place gradually, okay? And you could do kind of a middle index kind of thing as well. There's a number of different approaches to finding your first guess at a good index. So you could just pick it randomly if you want, but we just ended up doing this one over here. Okay? So that's just heads up. And there's the medium 3 thing I mentioned. So how you get your first guess changes a little bit, but the overall strategy of it is not going to change. So it is not stable. Randomness is a crucial improvement, and that can get us a best case of n log n. But like we said, your boss at Google's gonna want to know, like, what's the worst case going to be like, right? So the average case, if we randomize all the data, is n log n. But if we can't do that, we could degrade into a quadratic sort, which is not great because we saw last time that could be years instead of minutes. So this is one of the reasons quicksort probably isn't as popular as it used to be, because memory is so affordable, and things like merge sort are stable and work reasonably well. Okay, but on smaller devices, maybe it's okay. Okay, so we would say that is not tightly bound the way that the merge sort is. So again, worst case is often referred to as big O, okay? So we'll come back to big O and what we call these other things here in a little while. But we want to have an intuitive sense of what we mean by that before we kind of move into the mathy part. So let's just get one little insight and then we'll get to the lab. I love this because I just didn't know about this one for a while. So quick select is just a subset of the quicksort algorithm. And I like it even more than quicksort. This thing is really useful and does get used. So very often we want to know what is the kth largest thing counting from the bottom. So if I sort things and I say, give me the third largest thing, or you could say third smallest thing, depending on your perspective, the thing in position 0, 1, 2, that's the thing we're looking for. That's the third thing, right? So you might think we got to sort everything in order to figure that out, right? Or even the median. It's very important in data science to find the median, as you can imagine. And you don't want to be sorting like, the IRS, everybody's income, right? You want to find the median income, right? So how do you actually do that without resorting all the time, okay? So these things can be done in linear time with a relatively moderate change to our quicksort algorithm, okay? Which is pretty cool, right? Because if we sorted its n log n, that's pretty good, but it's not as good as linear, okay? So here's how we do that. So imagine this is our 0th value, 0 because of the position, not because that's the number 0, right? So imagine we had all these numbers that are not sorted, and this is what they look like sorted. But the positions that we're talking about are the 0th, the second largest, the median, right, 13th, whatever. We're referring to the ordinal position here, okay? So if we have duplicates, of course, the numbers are not going to be, right here, the 7 ends up in the 7th position, right? But with duplicates or gaps, who knows, right? So just to be clear, we're talking about the index positions here that we're interested in. The 13th largest means the 13th position, okay? So keeping that in mind, what we want to do is modify the quicksort. So we just ask ourselves, should we look left or look right? Just like your divide and conquer lab. So if I'm looking for something in the 15th position, but I just found something in the 4th position, then go right. Okay. So that's a pretty easy change to the code. So given n items, right, where we have n minus 1 positions, the maximum k that we're going to ever have is n minus 1. So that means the maximum recursive depth is going to be n minus 1, and that's linear. So that means we can find this position in linear time, right, with a little change. Okay, so we'll look at how we do that. Because we know that as long as we partition something, that one is done. Okay, so here's the algorithm. Okay, so sorry for the colors. I know it's kind of hard to read up there. You should choose better next time. So if I'm looking for the 3rd largest one or 3rd smallest, depending on your perspective, it's in position 2. That's what I want. Okay, so but I pick the left one to start, like we do, and I say, okay, partition. Okay, so now I've got this thing partitioned. Okay, I've moved the 13 here in its final resting place and did our little partitioning left and right. So we know the 13 is done, and now we ask the question, is position 12, the position, is that greater than the number 2 position? Yes. So we want to go this way. So we want to recurse that way. Okay, so it's to the left. So we break that down, find a pivot point, repeat that process, and on we go. Only going n levels deep to find that position. Okay, so we shuffle before, we set a high and low. We'll do it in a non-recursive way now, but it's still divide and conquer. Say, give me a partition place. If P, where we put the 13, is less than what, the K we're looking for, then update our low. This is kind of like what you guys were doing, right? Otherwise, update the high, right? And otherwise, we found it. Just return the value at that location P. Okay, so that says we found it. We found the 2nd or 3rd largest thing. Okay? So that is a linear variation on the quicksort algorithm to find the kth largest thing. It is really useful, really, really useful. Okay. And linear is always good. So this is what we call a trace. I'm not going to take you through it, but you can kind of see as we go through, we're looking for the 2nd largest, 0, 1, 2, depending on what you want to call that, 3rd or 2nd. Okay. And slowly, we, trace through using a pivot, 13, then 10, then 10, then 9, then 4, and we get it. Okay. All the way down there. That's pretty cool. It's not a big change. Okay. And linear is always a good thing. Okay. So on average, we're getting linear performance out of that, assuming that we get this thing split in half every time. Okay. And our comparisons, if we really count them up, are essentially 2n, which we consider to be linear. Okay. We throw away that coefficient and just say that's a linear thing. Better than quadratic. Okay. And we can use the geometric series to kind of prove to ourselves that that's what's going on there. We kind of saw a little bit of that before, but essentially it's going to be on the order of 2n. Okay. So there's our quick select. That's what that is generally called. Worst case, half quadratic, but with a shuffle, we're actually doing pretty good. Okay. Questions on K select? Okay, so let's step back and send this whole sorting module a packing. So these are all of our things we've talked about. Some of these we didn't really talk about. We talked about selection, insertion, shell, quick, 3-way, merge. We haven't talked about heap yet, but you can kind of see that, you have in-place things and not in-place things. You have stable things and not stable things, right? We have our worst case scenario, which is generally what we're interested in, right? And we want n log n as the worst case because we could do better, right? That means we'll never, in theory, if we prove it mathematically, we know we'll never, ever, ever have worse than n log n, okay? But you can kind of see that a quicksort could be quadratic n squared over 2, okay?
Is first sort only stable if you go down the left side first?
No, it's stable as long as you have that auxiliary memory. Yeah. So if you tried, and we used to try to do this as a homework problem, we'd say try to write merge sort without auxiliary space, without breaking stability. And there's a rumor that there's a way to do it, but whether it maintains n log n performance is questionable. So, but yeah, you will definitely do it as long as you keep that merge base stable, which you can do with auxiliary memory. But you can kind of see the gold standard we're after is n log n. And merge sort so far is the only one that's achieved that for worst, average, and best, you know. But mostly we care about worst case. And again, that was referred to as big O. It's just a phrase, and we'll explore that phrase. It comes from math. But when people say, hey, it's big O n log n, what are they saying? What are you talking about? They're just saying, you know, on the worst day ever, it's never going to be worse than n log n. Okay. Its best day, you know, is never going to be better than n log n, roughly, right? But we're kind of more worried about the worst case scenario because people start screaming at you when their servers go down and stuff like that. Okay? So nobody's really discovered a stable in place algorithm that is n log n. Maybe somebody will. Maybe one of you guys will. But there's a few things out there that have not been cracked yet. Okay? And we'll take a look at heap sort here. We'll circle back once we get into heaps in later part of next week. But really, we're kind of done with our sorting analysis here. And there's a lot more sorts out there. You know, they're all variations and hybrids and things that are pretty cool. But theoretical maximum seems to be around n log n. Okay. Hopefully, you kind of have a sense of what I mean by that in terms of the worst case. Okay. High level questions on kind of our overview of the sorts. Okay, all right, let's see if we can get you home. If you want to come back and study these, we got our Quizlet. I'll kind of keep an eye on that. And I think it's public, but if you want to join, you're welcome to join. I don't think I probably should just leave it public and let you just go. You can look at all the videos here. The links are here in the PowerPoints if you want to do that, or the PDF. And you can go sometimes. TopTal has some interesting tools and visualizations over there. Basically, do some pretty deep analysis and say, yeah, there's really no one best all-around sorting algorithm. And it's pretty interesting to visualize that stuff sometimes, but you don't have to, you know, spend too much time there. Lab 6 is our last for the time recursive algorithm. So this is recursive differences. So this is something I made up. I would like you to do a divide and conquer algorithm that kind of works from the bottom up, a bit like merge sort. So let me see if I can explain it to you this way. So if you have these numbers, what I want you to do is recursively start from 0 to position 3, calculate the midpoint, right? So the midpoint is 0 plus 3 over 2, always, right? Integer space. And then use that to recurse down the left side until you get to one thing, and then subtract those two things from each other and return that value up the chain. So 3 minus 6 is -3. Hand that back. And then as you return from that deeper level of recursion, you'll do the right side, and then you'll subtract the solution of one to the other, and you just keep handing that up and up and up and up. Okay. It's not exactly partial differences, you know, in terms of partial differences in math, but it's an interesting way to, you know, verify that you're doing everything right and you're handing something back the whole time. Okay. So everything's pretty much written for you, of course, except that little recursive differences function, and all the testing in main is kind of done for you. And there's really only one correct answer, I think. So your recursive diffs function looks like this. You know, right now there's nothing in there. So you're just going to keep breaking it down until you get down to a size of 1, and then you're going to return that thing. And if it's a size of 2, you're going to subtract it and return that thing. So you'll have to think about what your base case is going to be there. Okay? So your test answer is recursive diffs. You got to return the final sum of that kind of cascading thing. So here's an example just to work you through one of the squirrely cases. So these are even numbers. So your midpoint calculation is going to be 0 plus 7 over 2. Okay, 0 plus 7 over 2. That means 3 minus 6 minus 7 minus 5 minus, right? This is one recursive side, and this is the other recursive side, right? So you're going to work your way back up the chain. You should get a 1. So you can test that. Okay, that's test A. Test B has an odd number of things. So 11 things, right? 0 plus 11 over 2. That's going to give us our midpoint. Okay. And here's where recursively you just need a base case that deals with one thing. Don't try to subtract it from itself or anything crazy like that. Just return the 5, right? And so the final answer in that example should be a -5. So not a lot of code. It's not exactly the merge sort, but it's pretty darn close sort of structurally. So if you want to go back to look at your merge sorts, you can. But that's really kind of our recursive unwinding of each of these sides, okay? And our final answer. And that's it. Let me just see if there's any gotchas in the code real quick, and then I'll let you guys make a dash for the door. There we go. So I think you can do this all in the online compiler or copy the code down as you need. You don't need Pro, but you can if you want. Let me just see if there's any gotchas in here. Yeah, I think it's all kind of laid out for you. Yeah, pretty much just that, right? So I won't belabor that any more than it is. You can kind of see it. It's pretty straightforward. And that's it. So thanks, everybody. Hope you have a good weekend. I will be grinding away on your homeworks and have you all caught up by Sunday night. Okay. Hang in there. We'll see you next week, and we'll start talking about queues and priority queues and stacks next week, which moves us into data structures. Okay. Thank you.
Everybody have a good weekend.
Thank you. You too. Thanks. Thanks, everybody. Thank you.